the motion of an object. The motion of the object can be described several different ways. We can describe the motion of the object with words. We can describe the motion of the object with pictures, graphs, and equations. Today what we're going to be looking at is how to represent the motion of an object with something we call a motion diagram. Now, motion diagrams aren't difficult, and it's actually a nice way to represent the motion of an object. And so what I'm going to do is go through several slides of how to make a motion diagram, some of the pieces and parts of a motion diagram, and then you'll get a chance to practice. So first thing is motion diagram. And a motion diagram, if we'll take a look at this object here that I have, I've got a motion diagram, I've got an object that I start with. Let me move this box out of the way so that we can see it. So here is my object, and if you'll notice, that's what we always have to start with. We've got to start with an object. Now, the picture gives information that we start with. It could be a ball, it could be a car, it could be, in this case, a pool ball. But we basically have to start with a picture. This could also be the marks on your bubble tube. You've seen that before. Now, when we make a motion diagram, the first thing that we have to do is we have to define the positive direction. Now, the way we define the positive direction is with an arrow that looks like this. Now, you'll notice at the end of the arrow, there is an X. Remember that X in this unit is going to stand for position. And what we are doing is we are defining the positive direction to the right. Now, typically you'll see an X at the end of that arrow. Sometimes you'll also see a positive as well. Either way, essentially what we're doing is you are defining the positive direction as to the right. Now, standard in physics is you can define positive direction wherever you want as long as you define it. However, in this class, we're going to keep it simple, and therefore we're going to define right as the positive direction and up as also the positive direction. So, first thing you do is you define your positive direction, which we've done. Next thing that we've got to do is you have to include some kind of reference point, a reference point for positions. And that's what I've done here at the very beginning, is I've included a position reference point. So we would say that would be 0 meters. It doesn't have to be 0. You could make it 5, 10, 15, 20 if you want. I'm using 0 in this case just to show you a couple different ways that we may look at it. And essentially what I can do is I can tell that my ball is positioned at some number bigger than 0, the way it's written down. But once again, you need to have some kind of reference point so that it gives us kind of an idea of what we're comparing it to. Now, once you have your reference point and your positive direction defined, now a motion diagram really consists of dots. In this case, I'm going to only place one dot. We'll see a later example where we'll have multiple dots. But that dot is simply going to represent where that object is at a certain moment in time. So at one moment in time, that's where that ball is. And so that is the basics of a motion diagram. Now, what we want to do, though, is we want to make sure that you understand how to include when objects are at rest, how to include when objects are moving. So we're going to look at some other things. But the first thing we want to look at is if we have a stationary object, once again, we want to be able to tell what its starting position is. So if you take a look at the first picture has an object that is starting to the right of the reference point. We will call that positive. You could even say that that is a starting position at some number greater than 0, would be fine to include. Now, if you compare that to the other one, this object is starting at some number that is smaller than 0, or in this case is negative or to the left of the reference point. Now, once again, it's important to have that reference point on there because it lets us know if the object starts on the 0, if it starts at some number bigger than 0, or in the last case, if it starts at some number smaller than 0. Now, when we take a look at objects that are moving, we are also going to be looking at how those dots will change. And essentially, we look at the position of the object at regular time intervals. Now, if you think about what regular time intervals mean, it just means something regular and repeating, just like the metronome in the Bubble Lab. Or say I'm taking data every single second, or every minute, or every hour. Well, in this case, we have a skateboarder that is moving to the right. In this case, it would be in the positive direction. And the way we would represent a moving object is we would have multiple dots. So at each position, at each time interval, the position has changed. So this person starts off at the reference point, or 0 meter mark, and then a second later, they're at a different position. Another second later, they're in a different position. Another second later, they're in a different position, and so on. I think of this like a car with a drip coming out of the oil pan. And at each time interval, at regular time intervals, the car would leave a drip on the sidewalk. So in this case, this is a drip that's being left, and as the person is moving, then that drip just continues to leave a pattern on the pavement. Now, that is not a complete motion diagram yet. The reason it's not a complete motion diagram is it says nothing about how the object is moving. We know that the object has multiple positions at different time intervals, so we have to include the velocity in the object. When we include the velocity, remember, is the speed of the object plus the direction. So if you'll take a look at the arrows that are going to appear, the arrows in this are going to represent the direction it goes, and clearly you can see they point in the positive direction. The arrows also tell us how fast it's going. So if you'll notice, the length of each arrow is exactly the same size because I can tell that my velocity is constant. This object is not speeding up. This object is not slowing down. They are equally spaced. Therefore, each velocity arrow is going to be the same length. Now, there's a couple of things you should notice about the velocity arrow. The first one is that arrow fills the entire space between two dots, or one time interval. It's important to make sure it is the entire length. The other thing that you'll notice is I can very clearly see the tip of the arrow, so I know what direction it goes. So you don't want to be lazy about drawing your arrows between your dots. Now, once again, remember, velocity tells me how fast the object goes and the direction of travel. If my object were traveling slower, but at a constant velocity, then my velocity arrows would be shorter. If my object were traveling faster, then my velocity arrows would be longer, and so on. In this case, we are going to be looking at constant velocity the entire time before Christmas, so every one of our arrows will be the same length, at least for each section. Now, motion diagrams and graphs say the exact same thing. So if you take a look at the motion diagram that I have here, the graph that I have here, I know that my object starts at a starting position of 0 meters. I know that my object goes in a positive direction because I have a positive slope. I know that my object does not speed up or slow down, but instead travels at a constant velocity. I know this because it is a constant slope. Now what I can do is I can take my graph and I can turn that into a motion diagram. Now if you'll take a look on the side, what I'm doing is I'm just simply putting the dots at regular time intervals. They're equally spaced, and they, in this case, are going in the positive direction, which is up. The last thing that I do for my motion diagram is I then put the arrows in. Okay, so the motion diagram isn't something that is just pulled from nowhere. The motion diagram actually is translating the information from the graph. Now, if I have an object that's standing still, I know that they're occupying the same position over and over and over again, and I can't really put a dot in the same place over and over and over again. So the way we represent an object standing still is with dots that are stacked. Now, don't think that this object is moving up, because it's not. Remember that the position is across the bottom arrow anyway. These are just time intervals that are happening, and it is occupying the same position at the bottom, which is some number bigger than 0. Now, if you'll notice, there are no velocity arrows when I have an object standing still. So think about that. Why would there be no arrows between my dots? Because I have zero velocity. My object is standing still. It's not speeding, it's not moving at all. So therefore, if it's not moving at all, then it would have zero velocity. So I would not put any arrows between the dots because the arrows represent velocity. Now the other thing that I can do is I can look at objects that are traveling up. And if they're traveling up like this balloon is, just take a look at the motion diagram that gets left behind. And I want you to think about a description. Now remember how I said at the beginning you can describe the motion in words. You can describe with motion diagrams. You can describe with graphs. So if I were looking at this particular picture motion diagram, and I were going to describe it in words, my starting position, or my XI stands for initial position, would be 10 meters. And I can tell that just simply by looking at where the object is starting at the bottom. I know the direction of my travel is a positive direction. I know it's a positive direction because I've defined up as the positive direction with my X at the top. I know that it is traveling a constant velocity. I know that it's traveling a constant velocity because every single arrow is exactly the same size. And because I don't have anything to compare it to, I'm going to say this is medium, a medium rate. Now, the description of motion is a little easier whenever you have something else to compare to tell who's fast, who's slow, who's medium. So in this case, it feels a bit arbitrary. However, if the object were traveling slower, then the arrows would be shorter. The velocity arrows would be shorter. If it were faster, then the velocity arrow would be longer. Now, number of time intervals we really haven't talked about yet. So if we take a look for the number of time intervals, I want to look at my time, and I'm just going to count it out. And I'm going to do this a couple different ways. Now, first thing is, let me grab my pen. All right, so the first thing is, if you think back to the Bubble Lab, this first mark that we made was called time 0. And so this was time 1, this was time 2, this was time 3, and the last one is time 4. So that's one way you can tell the time intervals. There are 4 time intervals. I find that sometimes that gets a little confusing. So the easiest way is to count the time intervals, which would also be counting how many arrows you have. I have 1 time interval, I have 2 time intervals, I have 3 time intervals, and I have 4 time intervals. So if you look at that way, I think it's a little bit easier to figure out the number of time intervals that happen. Now, we don't know if this is seconds, minutes, or hours. We're just going to call it a generic time interval. So here's an example to try. And with each one of these examples, I want you to think about the description of motion in words. What is the starting position? What is the direction of travel? What is the type of motion? What is a qualitative description of motion? And what is the number of time intervals? So look at the picture. Starting position is some number bigger than 0. We don't know what that number is, we just know it's some number bigger than 0. Some students may decide to make up a number that's bigger than 0, or simply saying that the starting position is some number bigger than 0 or greater than 0 is fine. Now, the object is traveling in a positive direction. I know that because the positive direction has been defined. I know that it is a constant velocity because each one of those cars are equally spaced. And I'm going to say that those are fairly slow. They look pretty close together, so I'm going to say it's fairly slow velocity. And the number of time intervals, remember we just said, would be 1, 2, 3. 3 time intervals because I have 3 spaces between my cars. Or you can count it out. The first picture is time 0. Second one is time 1, 2, then time 3. Now, motion diagram. Think about what the motion diagram would look like for this. and then compare it to this one. Now, the motion diagram on the second one, my starting position is also some number bigger than 0. But I can tell that it's a bigger number than the other one. In this one, I can also tell that I'm going in a negative direction, constant velocity, but you can also clearly